Hi, welcome to the course Electric Circuit Theory. Today we'll study part 4 of chapter 1, Network Analysis, and the topic of our today's presentation is electrical resonance. When the voltage applied to an electrical network consisting of resistance, inductance, and capacitance is in phase with the resulting current, the circuit is said to be resonant. That means for a circuit to be in resonant, the applied voltage should be in phase with the resulting current. The phenomenon of resonance is of great importance in all branches of electrical engineering, such as radio, television, and communication engineering, since it enables a small portion of the communication frequency spectrum to be selected for amplification independently of the remainder. At resonance, the equivalent network impedance Z is purely resistive since the applied supply voltage and current are in phase. And the power factor of a resonant network is unity. In the electrical engineering, there are two types of resonance. One is series resonance and the other one is parallel resonance. In case of series resonance, the input impedance is a minimum. And in case of parallel resonance, the input impedance is a maximum. Let's start with resonance in a series RLC circuit. Here we can see a circuit in which resistor, inductor, and capacitors are in series and are connected to a source with voltage V and frequency F. So in this case, in this circuit, we can write the total impedance Z as Z equals to R plus J XL minus XC. And we can write XL as omega L and XC as 1 by J omega C. Here, omega is 2 pi F, where F is source frequency, and omega is angular frequency of the source. In this case, we can easily see that this XL equals to omega L and XC equals to 1 by omega C. And in this case, XL and XC both are frequency dependent, and XL increases with increase in frequency, but XC decreases with increase in frequency. So at a particular frequency, the inductive reactance becomes equal to the capacitive reactance. This inductive reactance XL becomes equals to capacitive reactance XC. In such a case, this imaginary part cancel out. So Z will be equals to R. In all the other cases, there will be real as well as imaginary part of impedance. But in case of resonance, since imaginary part becomes 0, the impedance Z will be minimum, which is equal to R. In this case, since impedance is minimum, the current attains the maximum value. So when XL equals to XC, the applied voltage and the current are in phase. This effect is called series resonance. At resonance, since XL equals to XC and since this inductor and capacitor are in series, that's why VL will also be equal to VC, since same current flows through both of these components. And impedance Z will be equal to R, which is the minimum circuit impedance possible in an RLC circuit. And the current will be equals to V by R. That's the maximum current possible in a series RLC circuit. Current will also be maximum. And since XL equals to XC, we can easily write 2 pi FL equals to 2 pi FC. And this gives frequency, that is a resonant frequency, which is equals to 1 by 2 pi squared of LC. And this FR is the resonant frequency. This figure shows the phasor diagram of RLC series circuit at resonance. Here, we can easily see that since the values of since the magnitude of VL is equals to magnitude of VC, but they are in out of phase, so they cancel out each other. And what remains is only VR. And the value of VR will be equals to the source voltage V. And since the source voltage V is equal to VR, we can see that the source voltage is also in phase with the source current. Therefore, the circuit current is in phase with the applied voltage, and the circuit behaves as simply a resistive circuit. When circuit is in resonance, the current is too large, and because of the large value of current, the voltage drop across inductor and capacitor in a series resistance circuit will be very high. Although they are very high, since they are equal in magnitude, they cancel out each other. And um, but the voltage, with very large voltage drop across inductor and capacitor sometimes it may result in very high voltage in case of transmission lines. That means it is one of the causes of high voltage in transmission line. If the resistance R was not present in the circuit, then in such a case, there was great chance of short circuit during resonance. Since in this resonance, that means in case of series resonance circuit, the voltage is maximum, it is also referred to as voltage resonance. The series resonance circuit is also called an acceptor circuit because such a circuit accepts current at one particular frequency but rejects current of all other frequency. That means it only accepts current at a particular frequency. That's why this type of circuits are used in receiving antenna as well as radio receivers. Thank you.